So far we have been looking at the problem of the optimal separating hyperplane in the previous two modules, but then the idea of support vector machines is to be able to use it in data which is not nearly linearly separable or only working in the space of linear hyperplanes, right. One way of looking at extending this problem to complex complex settings is to think of taking your original data, right, and transforming it into something else and then trying to apply the same idea to the transformed function, right. This idea should not be pretty new to you, because we have already seen this in linear regression, where you can look at transforming the input variables into some other kind of basis functions and then trying to do a linear regression on that. So, the idea is similar to that, but we are going to make use of a very powerful technique here, right. So, look at how the predictor is going to work. So, you are going to have f of x equal x transpose beta plus beta naught. So, that is your predictor, and if f of x is lesser than 0, I will predict it as class -1. If f of x is greater than 0, I will predict x as being of class +1, right. And so, this is the separating hyperplane that we have, right. So, if you think about it, we said our solution betas, right, are going to be of this form, right. Therefore, I can rewrite this as right. So, if you look at it, interestingly, so x, all the x's, right, here appear as x transpose xi, it is essentially an inner product of the x's. And similarly, if you look at how we are solving the optimization problem, this is what we wrote down last time. So, the dual is essentially going to have again xi transpose xk, right. So, you can see that the x's appear in our problem always as inner products, right, and if you are somehow able to compute these inner products efficiently, then we should be able to solve the problem more efficiently. In particular, given that we are going to be looking at this kind of a transformation, right. So, I can now write this as where this denotes the inner product. This denotes the inner product. Right. So, likewise, the dual also can be written as So, if you stop and think about it, it essentially tells you that I really do not need to know h of x, right. If I have an efficient way of computing the inner product of the transform function, right, I really do not need to know what the actual transformation itself is, right. Okay. So, there is a class of functions which I am going to call as kernel functions here. is going to call as kernel functions, which allow you to compute this inner product efficiently. So, essentially it is going to say that so the kernel corresponding to the function h, right, when you give it as input x and x prime, it is going to compute the inner product of h of x and h of x prime. Okay. So, one of the things that we require for a function to be a kernel function, right, is that it should be symmetric, right. So, k should be symmetric positive definite. So, if you do not really understand that, so k should be symmetric in the sense that if I give it a set of x and x prime, so the kernel function for x and x prime should be the same as x prime comma x. Okay. And positive definite essentially means that if I take any vector x transpose kx, okay, that should always be positive. So, there are technical reasons for why these conditions should be satisfied, but one rough way to think about it is to say that, hey, this essentially you would want this to be, this whole thing to be positive, so that your optimization problem will work as you want it to. Okay. So, that is rough intuition behind why you need these conditions. Some of the popular choices for the kernel functions are the polynomial kernel, it is essentially 1 plus right, where the parameter d is something that you choose. The other one is the Gaussian or the radial basis function. The other one is sometimes called the neural network kernel or the sigmoidal kernel. So, what do these kernels buy you, right? So, as I was mentioning earlier, you have your data that is given to you in the original dimensions, right. The data might be badly mixed up in that original dimension, it might not be easily separable at all in the original dimension, but then when you look at a transformed dimension, then the data becomes linearly separable, right. So, let us take the example of the polynomial kernel and see what happens. So, I am going to look at a polynomial kernel of dimension 2, right. It is essentially 1 plus So, I am assuming that the vectors x consists of x1, x2 and x prime consists of, right. So, these are like 2-dimensional vectors and on which I am defining a 2-dimensional polynomial kernel. So, this is the dimensionality of the kernel does not necessarily have to match the dimensionality of the underlying space, but in this case I am assuming it does. So, if I take the square of this, right, so I essentially end up with a expression that has 6 components to it, right. So, if you think about it, this is somewhat like taking the inner product in a very in a higher dimensional space than the original space. So, originally x and x prime were residing in a 2-dimensional space, but if you look at what is happening now, it is essentially something like this. So, h of x is 1, h1 of x is 1, h2 of x root 2 of x, root 2 of x1 the first coordinate, h3 of x is root 2 of x2 the second coordinate, h4 of x equal x1 squared, h5 of x x2 squared, h6 of x root 2 into x1. So, if you imagine that I transformed my original 2-dimensional representation into a 6-dimensional representation, it is essentially taking all the second order terms along with the original terms, and now if I take the inner product of h1 of x and h2 of x prime, I will exactly end up with this expression, right. So, inner product of h of x and h of x prime, right. So, the entire 6-dimensional vector, if I take the inner product, I am basically going to end up with this expression. So, what we have done here, we took the inner product in a 2-dimensional space, right, and performed a squaring operation. So, that is going to give me a number which is equal to the number I will get by first transforming the data point from 2 dimensions to 6 dimensions and then taking the inner product in the 6-dimensional space. So, essentially this allows us to work in a much higher dimensional space than originally intended, but by only looking at inner product computations in the original space, right. So, why is this a useful property to have in the case of support vector machines is that all our operations here operate only with inner product, whether we are finally trying to predict the output f of x or when you are trying to solve the dual problem LD. So, all we really need to do is know what the inner product is, right, and now I am able to take the inner product in a higher dimensional space, but then do the computation only in the lower dimensional space, and this allows us to have a much greater advantage than simply operating with the original dimension. So, to see how this polynomial transformation really helps us, let us look at a very simple example, right. So, I am going to assume that as a single dimension, right, and then I have data points, let us assume that this is 0, I have data points that look like this, right. So, this is the dimension x1, right. So, obviously there is no single line that I can draw to separate these into 2 classes neatly, right. So, I can assume my slack variables and try to draw a line here that says okay I am not making too many errors blah blah and so on and so forth, but still that is not the that is not a satisfactory solution. But let us look at what happens if I try to plot this data in a 2-dimensional plane where I have x1 as one of my axis and x1 squared as my other axis. Okay. So, the 2 zeros will probably get mapped to somewhere here, right. So, that will be the x1 that is corresponding to this here, and then I am looking at the square of that. But then if you look at these data points, so this is going to go here, this will probably go here, right. Now it is very clear that I can draw a straight line, right. I can draw, if I can find a linear decision boundary that separates these two classes once I have done the appropriate transformation. Right. So this is essentially allows us to solve a larger class of problems using such kinds of basis transformations than we could do just by operating in the original place and trying to solve the linear optimal hyperplane problem. So this is essentially what all your choices of kernel functions are all about, right. So if you look at any SVM tool, they will tell you to pick one kernel function, which is either the polynomial kernel, so in which case you have to pick an appropriate D, or you have to pick a radial basis function or a Gaussian kernel, in which case you have to pick an appropriate gamma that tells you how fast the Gaussian is going to decay, or you can pick a sigmoid or a artificial neural network kernel where you have to pick kappa 1 and kappa 2, which are the parameters that define how quickly the sigmoid function rises. So we will see more about that when you look at neural networks. Right. So apart from this, you still have one further parameter that we will have to worry about, which is this constant C, right. So this tells you how much slack that you are willing to tolerate, right. So if you think about it, if C is very large, if C is infinite, right, then you have to be in the completely separable case, because even a very small value of zeta, right, will cause this objective function to become very large, right, even for a small value of zeta, right. So you will find that this thing is actually very bad, right. So C has to be, if C is very large, then zeta has to be very small, right, and if C is small, then zeta can be large. So what is this going to tell you is that in the higher dimensional space, right, so we are assuming that the higher the dimensionality that we are projecting into, the more likely is it that the data will be separated, right. Because of that, if C is large, right, because you are going to try and fit a more complex surface, right, the surface will look very wiggly, right, and if C is small, then you are going to get a much more smoother surface, but the possibility of you making errors is also higher. So that is a trade off that you have to figure out empirically by looking at how you are doing the how we are performing in the actual data. So this brings us to the end of the module on support vector machines, and these are very powerful classifiers, and quite often they are the first classifiers of choice for people when they are trying to solve a new problem about which they really do not know much. So one thing I should point out that people have come up with different kinds of kernel functions. So I have given you 3 choices of kernels here. These are essentially the most popularly used kernel choices, especially if you are operating with text data, you would like to use a linear kernel where D is 1, and in most other forms you will be looking at RBF kernels. But then for special forms of data like graphs and strings and so on and so forth, people have defined their own kernels, and as long as they are satisfying your properties of the kernel function, you can define your own kernels and then have them help you in solve the problem, right. But that is a topic for another day, or perhaps for another course. And so we will stop here. Just let me reiterate that SVMs are one of the most popular and powerful classifiers that are currently being used widely.